Hello, this is Chuck Ridgway, Automation Technology Manager here at Horner. Thanks for joining us for another Tuesday live stream. Well, we're now in November, and October was one crazy month. We had 5 Tuesdays, which meant 5 programs for you. I had a crazy travel schedule, and I unexpectedly caught a mild case of COVID, so that knocked me out for a while. So we had a lot of pre-recorded videos last month, but in November, many more of them are going to be live, just like today. Okay, so here's the topic we've got for you today. Precision timing using the Horner OCS High-Speed Counter. Now, for those of you who watched last week's program, we were just being silly, let's face it. So we decided instead of having a serious topic like we normally do, we just did kind of a spoof of a show where we had a little bit of fun dropping pumpkins from the roof of the Horner headquarters and timing how long those pumpkins took to hit the ground and how fast they got. It was just a lot of fun. Now, believe it or not, behind the silliness, there was a bit of application programming that we did. So when we dropped the pumpkins from the roof, we used a couple of sensors to time how long it took for the pumpkins to go from point A to point B, and we used the Horner High-Speed Counter to do some precision timing and then some math to convert that to velocity. So today, even though you may not have a plan in the future to make, pumpkin velocity part of a future application, you may need to do some precision timing, and you might want to try out the Horner High-Speed Counter to get that done. So that's the plan for today. Now, I'm flying solo today because Casey Gardner still isn't back in the office because there's been a new addition to the Casey Gardner family, which we might be asking him about next week. But for now, let's dive into the topic and let's take a look at how we're breaking it down. Okay, so we're going to answer the question, what is a high-speed counter and when should you use one? We'll do a quick review of the capabilities of the high-speed counters that are built into the Horner OCS. We're going to identify fully from an application standpoint what today's problem is, and then we're going to plan and execute the solution that we came up with for the Pumpkinator 5000 last week. But there's some good application nuggets in there that I think you'll get a lot out of. So what is a high-speed counter function? Well, effectively, a high-speed counter is a special function of a PLC or an OCS all-in-one controller, and that special function depends on special hardware circuitry built into the PLC or built into the OCS that allows some of the inputs and outputs to be processed outside of the logic scan of the PLC or the OCS. So this allows events which might occur much faster than the controller scan rate to be handled accurately. And now the specific high-speed counter functionality that's available for any PLC or OCS is going to vary by controller, so you always need to pay attention to the capabilities of the particular controller that you're using as you plan out your application. Okay, so when would you use a high-speed counter function? Well, there's a whole bunch of situations when you would, and here's some examples. So the most obvious one is when you're going to be counting pulses that are on for a very short duration. So maybe you've got a pulse train that's maybe about 5K or 2K or 10K, maybe even just 1K, and you're trying to count those pulses, and obviously they're not on for very long. And if you just wired that device to a regular PLC input, you're going to miss a lot of transitions. So that's an obvious one there. Similarly, if you're measuring frequency accurately and it's a fairly high frequency, you're going to need to use a high-speed counter. Now, for today's program, we're using a high-speed counter because we're timing an event where each millisecond is important. So we can't just use built-in PLC inputs and built-in timers and counters in the logic program. And then another good example is maybe when you want to fire a digital output, a solid-state output, when an encoder reaches a specific target position. That's another case when you might need to use, or you probably will need to use, a high-speed counter function. Now, what all of these different examples have in common is that in all of these cases, if you just wire these signals or these applications up strictly to your standard PLC inputs, you're going to miss signals and you're going to inaccurately time events or capture or trigger events. So that's the commonality you'll see between all those different examples I gave you. Okay, so last week, our application problem was how fast is this object moving? And that object that I've got highlighted there is a pumpkin that we dropped from the roof. So just before we get into some of the more serious stuff, I'll show you a couple replays of some of the drops that we did last week. Here you can see it in real time, and here we've got in super slow-mo. So I'd like to say that there were no pumpkins harmed in the testing we did last week, but unfortunately that would not be accurate. As you can see from the shells and the seeds that are speeding around and littering all over the ground there were absolutely some pumpkins that were harmed in that testing. Okay, so let's head back to our application problem. So effectively what we did last week is we needed to measure the average velocity of the pumpkin as it passed between point A and point B. And point A was the top of the roof and point B was the ground. Now, even though in some of our silliness, we kind of pretended to put an accelerometer on the pumpkin at one point, for a bulk of the testing we did, there was no sensor attached directly to the pumpkin. We strictly depended on a photo eye at the top of the roof and another one on the ground. And the idea being that we would time very accurately how long it took for that pumpkin to get from point A to point B. Now, let's say we were going to solve this application without using the high-speed counter function. How would we do that? Well, effectively, what we would do in that scenario is we would connect the two photo eyes, the one at the roof and the one at the ground. We would connect those to standard PLC inputs, all right? And then as soon as that first photo eye input turned on, we would start a 1 millisecond retentive timer, for instance. And then as soon as the second photo eye turned on, we would stop that timer. And then as long as we had a retentive timer, that accumulator value would tell us down to the millisecond or so how long that took. So that seems like a reasonable approach to solving that problem. And it would truly work if your distances between A and B are large and your object is moving very slowly. In that scenario, you know, the scan rate of 5 or 10 milliseconds or whatever it happens to be for your application would be insignificant as compared to the measured times. However, as we were dropping these pumpkins from the roof, the distance between A and B wasn't very large. It was only about 4 meters, and the pumpkins were traveling pretty quickly. So strictly using the PLC method was not going to give us a whole lot of accuracy. Certainly not accurate enough for the Pumpkinator 5000, and so that's why we decided to use the high-speed counter function. Now, before we dive into the specifics and how we set up the high-speed counter and how you might do something similar in a future application, let's review a little bit the high-speed counter functionality or capabilities, if you will, between the different OCS product lines. And this is true even if you're using a PLC. You always need to understand specifically what the high-speed counter capabilities are with your hardware. Okay, if you're using some of our lower end products, still very capable, but of the lower end of our product line, like the XLE and XLT and the Micro OCS series, you'll find you have 4 high-speed counters available, and you can do all kinds of functions. You can do totalizing, which is counting. You can do frequency measurement, pulse measurement, and you even can connect an encoder and use quadrature mode. Okay, so that's a pretty good capability. But if you're using our higher end products, like the XL series from the XL4 on up, including the X5 or the Prime series and the future Canvas series, you'll see there's a bunch of additional capability. So in addition to supporting higher frequencies, we also add high resolution timing and flexible real-world input triggers for disable, latch, preload, and clear. You'll also be able to fire real-world outputs based on high-speed counter accumulator values. That's another key capability. So as you can see, the XL series, XL Prime series, those higher end products have a little bit more capability. And specifically in our application, because today's problem is one of precision timing, we're going to take advantage of the high-speed timing capability of the XL series and above high-speed counter. So we decided for the Pumpkinator 5000 that we would use the EXLW. It was a controller we had sitting around, and it has the enhanced high-speed counting capabilities. Okay, so how are we going to set this up in the OCS? Now, I'll go through all the detailed configuration in a bit, but let's go ahead and show you through a couple of slides first. So as I just mentioned, we're going to take advantage of a special mode of the totalizer of the high-speed counter where we can effectively count 10 megahertz pulses that are generated by an internal clock. That gives us the ability to turn our high-speed counter into a high-speed timer and use those capabilities. Now, what we're also going to do is we're going to take our photo eyes, A and B, and we're going to wire them in not just to any regular old input, we're going to wire them into one of the 4 high-speed inputs. And in the XL series and XL Prime series and the future Canvas series, those are labeled as H1 through H4 on the terminal strip. And then from a memory map standpoint, those are I9 through I12. So those are the high-speed inputs that are physically connected internally in the OCS hardware to the high-speed counter circuitry. So the result we're looking for is that our high-speed counter is going to be sitting there counting up in 10 megahertz increments, and we're going to somehow use those 2 photo eyes to capture and measure the elapsed time. Okay, so now there are 4 high-speed functions that are kind of in our toolbox for any high-speed counter application. And these are disable, latch, preload, and clear. And for every high-speed counter application, you can decide, do you want these functions to be performed by an external real-world input connected to one of the high-speed inputs? Do you want it to be an internal function triggered by a variable that's mapped to a Horner internal memory point? Or do you just want to disable that feature for that application because it's not really needed? Now, the 4 different functions do as follows. You have the disable function, which will disable the high-speed counter from counting. You have the latch function, which will instantaneously take the current value of the accumulator, copy it away to a different location where it can be accessed later. You've got the preload, which you can use to effectively set the accumulator to a specific value, and it's typically a non-zero value. So maybe your machine is at position 10,000 and you want to load the 10,000 into your accumulator and then take off from there, for instance. And then the clear function is pretty self-explanatory. When that's active, the accumulator is set to a value of 0. Okay, so let's set about solving this problem by first thinking about it like we were doing it using just the standard timers that were built into the PLC, and we were wiring everything to a standard PLC input. So could we make the high-speed counter work such that the counter would start timing, counting 10 megahertz pulses when the first photo eye is triggered, and stop timing or counting when the second photo eye is triggered? Well, to do that, I think we would have to utilize the disable function very creatively. So we would have to connect the disable function to a real-world input, and somehow we would have to make the disable function turn off whenever the leading edge of that first photo eye is triggered. And if we go into the configuration under the disable function, yes, we can connect it to an external input, but the only choices we have are either to, enable the disable function or turn on the disable function when the physical input is high, or turn off the disable function when the physical input is off. So that's really not the flexibility we would need to kind of configure it this way. So we're going to abandon this first thought, and that is of making the high-speed counter work exactly like it was just a regular PLC type timer. Okay, instead, what we're going to do is as follows. So we're going to utilize enable, but we're going to use it as an internal function. So we're not going to use an external real-world input to enable and disable or to turn on the disable function for our high-speed counter. We're going to do that internally in our program. And the reason we're going to do that is because, enabling and disabling isn't necessarily critical from a timing standpoint. Because what we're going to do in this scenario is when we turn off the disable on our counter, allowing it to start counting, we're going to make that kind of non-critical from a timing standpoint. And instead of using that to kick off the start of the elapsed time calculation, if you will, instead, while the counter is busy counting, we're going to use the clear function to be connected to the first photo eye. So the high-speed counter will be not disabled. It'll be sitting there counting up in 10 megahertz increments. And then when that clear input turns on from the first photo eye, it's instantaneously going to go to 0, but then continue right on. And then therefore it'll be counting up from 0 until it hits that second photo eye, which we're going to assign to the latch function, and then we'll get the result we want. The elapsed time in 10 megahertz increments will be contained in the latch register. So that's where we'll actually see the result of our experiment, if you will, or the result of our calculation. Now, this can only work if both the clear and the latch functions can be active on the leading edge of those switches, because that's what we want to happen. When we first hit that first photo eye, we instantaneously want to clear and move on. We don't want it to stay cleared while that switch is on. We want it to continue on. So we care about the leading edge of that input. And similarly, when that pumpkin hits that second photo eye, we want to instantaneously do our latch function. Okay, so that's what we're looking to do. And as we go into the high-speed counter configuration block, and I show you a screenshot of that, you can see we can configure it exactly as I have just described. So we can assign disable as an internal to an internal bit, which we can then map to a variable. We can assign the clear to our first external high-speed input. We can assign the latch to our second high-speed input, and then we can assign both those high-speed inputs to be active on the rising edge of that signal. So that's what we're looking to do there. Okay, now when we get to actually, getting into our program after we've done the configuration and we need to start creating variables and using those in our program, the first thing we're going to have to do is go to the user's manual of the specific controller that we're using and find the high-speed counter memory map. And I've just got a snippet of it here for the EXLW counter number 1, showing the memory map for the accumulator, for the latch value, if you will, and then for the latch, preload, clear, and disable functions that are mapped to %Qs, whereas the accumulator and latch values are mapped to %AI registers. Now, in our application, there's some key variables we're going to need to utilize. So we definitely care about the latch value because that is where our resultant elapsed time is going to be in 10 megahertz increments. So we're going to need to create a variable that we map to AI403. That'll be our latch value as a double integer. And then because in my case, I've chosen to disable and enable the counter to start and stop it from logic, I'm also going to need to create a high-speed counter disable variable and map that one to Q1604. Now, I'm not going to assign variables for the latch, preload, and clear for the Q bits, because those are going to be handled, certainly the latch and the clear are going to be handled from the real world side of things. Now, one last note here, and that is this. I still want to be able to see the status of the top and the bottom photo eyes, even though they're directly wired into the high-speed counter circuitry. I still want to be able to tell if those are on or off or not, because I might need that elsewhere in my program. So I go ahead and create variables for those two photo eyes and map those into I9 and I10, because I'm using the first two high-speed inputs, H1 and H2 on the terminal strip, and that's where those are mapped in the real-world memory. Now, that does not impact the operation of the high-speed counter, but that way I can monitor and follow along what those switch states are at any given point. Okay, and then once I have the elapsed time in 10 megahertz increments, then it's just more or less simple math, because remember, the distance between the two photo eyes is a constant, a certain number of inches, if you will. And then if I want to take my 10 megahertz increments from my latch value and convert that to milliseconds, which is a convenient unit for applications in the automation industry, I just need to divide that value by 10,000. That'll give me milliseconds. If I want velocity in inches per second, I take the fixed distance between A and B in inches, divide it by the number of milliseconds, and then multiply by 1,000 to get my milliseconds over to seconds. And then to convert to miles per hour, I just divide inches per second by 17.6. And yes, I just Googled that. I could have figured it out, but I just decided to Google it instead. Okay, so let's go ahead and take a look at how we've set things up in Cscape and how things look here on the bench for our Pumpkinator 5000. All right, so let's take a look at the bench first. Okay, and here we go. We've got our EXLW with our Pumpkinator 5000 program, and I'm just using my handy dandy IO simulator to wired up to the first two switches. So I have switch number 1 connected into the first high-speed input. Remember, that's acting as the clear. And I have switch number 2, toggle switch number 2, connected to the latch high-speed input number 2 on my Pumpkinator, so that I can, again, perform the latch function as my pumpkin falls from point A to point B. So that's what things look like on the bench. All right, let's go back to Cscape now, and let's take a look at our program. Now, with the high-speed counter, you always start with your I/O configuration. So let's take a look at that I/O configuration. So here's my EXLW. I need to go to the local I/O tab. I select the config button on the I/O area here. I go to module setup, and I go to the digital in/high-speed counter button. And this is all the setup that's available for my high-speed counter. Now with the XL series, you've got 2 counter mode and 4 counter mode available. And I believe with XL Prime, I think the default is just 4 counter mode. I'm not 100% sure on that, but I'm pretty sure that's the case. We can configure whether our inputs are positive logic or negative logic, and that impacts all the inputs, not just the high-speed inputs. We have our standard memory map, or a default memory map for all the different high-speed counter functions. Now, in almost every case, you're going to leave these exactly as they are. That way, all the tables in the user's manual will match these references exactly. So it keeps things nice and simple. Now, you also have some filtering capabilities that I'm not taking advantage of here. Now, if I was installing this in a real machine, I probably would go ahead and do a little bit of filtering to prevent signal bouncing on my photo eyes. That would be something I would probably do, but I didn't do that in this case. And then down here at the bottom, that's the screenshot I showed you earlier. That's the configuration I'm specifically using for this application. So I am using a totalizer or counting mode instead of one of the other modes that you can see here. Okay. And then I'm using a special mode, which is counting internal 10 megahertz clock pulses. Now, there's also a 1 megahertz mode, and that would have been ample for this application, but I selected the 10 megahertz instead. And then down here is where we decide where do we want our disable, latch, preload, and clear functions to come from. Our disable function, we're going to use that as an internal variable. And then our clear and our latch are going to be external high-speed input number 1 and external high-speed input number 2, respectively. And we're going to be acting on the rising edge of these signals because that's how we want it to work in our application. Whereas maybe in other applications, we might want a falling edge or a high level or a low level instead. Okay, but we want rising edge in this case. All right, so that's our configuration for the high-speed counter. Now let's take a look at kind of how we've created our variables here. So let's go down to our program variable table. And the first thing you're going to see is the high-speed counter disable function, which we chose to do as an internal variable as opposed to an external real-world physical input. So we've created a Boolean variable and we've mapped that to Q1604. Why Q1604? Well, that's the default memory address for the internal disable when you look at the EXLW high-speed counter chapter of the user's manual. So again, you're going to need to reference that user's manual. I went ahead and created a variable of double integer type, unsigned double integer, for the accumulator. And again, from that table in the back of the manual, that's at AI 401. And then I also created the key latch variable. That's where our elapsed time value is going to reside. And that's in AI 403. Now, for my photo eyes top and bottom, remember, those signals are physically wired into high-speed counter inputs H1 and H2, but I'm still interested in knowing when they turn on and off. So I'm going to go ahead and assign %I9 and %I10 here so that I can follow along and see when those switches turn on and off because I might want to use those elsewhere in my program. Okay, so that's what my variables look like. All right, now let's go back to the bench. Let's look at the Pumpkinator 5000 in action, see how that all works at runtime, and then we'll come back and take a look at the logic. Okay, so let me switch over to my bench view. All right, here we go. So this is my main screen. So this first button represents the first photo eye, and this is the second photo eye, number 2. So I'm going to first need to enable the test, which effectively turns off the disable to the high-speed counter, and I'm going to do that from the screen. Okay, so now my test has started. Now my pumpkin hasn't reached point A yet. Okay, that will be found whenever I flip this first switch. Okay, and then it'll reach point B when I flip this second switch. And then because it took, quite a while for that to happen, you can see my pumpkin was only going at 2.75 miles per hour. Now, if this pumpkin was dropping from the sky, that wouldn't be very realistic, but maybe if it was going sideways or something, that might make sense. Okay, so that is kind of what it looks like from the main screen of the Pumpkinator, but let's go under the hood a little bit and see how this thing works with a little more detail. Okay, so this is the screen where I describe, or at least where I enter in, what is the distance between points A and B, which in my case, this is the drop height that we're talking about here, okay? And then on this screen, This is where we get to follow along and take a look at the values in the accumulator and the latch value, as well as the results of our calculations. And what you're seeing here on the screen, this is the results from the previous trial. So let's go ahead and run a trial from this screen. I'm going to go ahead and start by enabling the high-speed counter. You can see that the accumulator value just took off from wherever it was. It didn't clear first, it just took off from wherever it was. And then the results at the bottom are zeroed out, but that was caused by logic. Okay, so we're waiting for that first photo eye to turn on. And then once that happens, we'll be waiting for the second photo eye. So let's go ahead and, I guess, release our pumpkin. Okay, so here's point A and here's point B. Okay, so as you can see, our accumulator kept going until the high-speed counter was disabled automatically by ladder. But the latch value there is the actual value in 10 megahertz increments when that second photo eye was first tripped. Now, one thing you'll notice is that the accumulator value is different than the latch value. That's because it kept on going. So one way you can look at this is you can see that our trial took about, a little over 1,000 milliseconds. At the bottom there in the lower left-hand corner, you can see 1,060 milliseconds. But if we depended on freezing our accumulator through a real-world logic input, you could see we would not have accurately gotten that information. It would have been off by, quite a few counts there, as you can see. So again, what happens is, let's run it one more time. We enable our high-speed counter. The accumulator just takes off and goes from there. The first switch does a clear. The second switch does a latch. Okay, now, one thing you'll notice here is that the accumulator and the latch value are matching. Why is that? Well, it's because I did a lousy job of flipping that second switch. My second switch bounced, and that's why they're the same value. So that's why I mentioned earlier that I really should have done some filtering in my high-speed counter inputs to prevent this from occurring. Now, it doesn't hurt anything. It didn't negatively impact the latch value at all, because that was truly the value when we first hit. But again, a little bit of filtering would have been appropriate in this case. Okay, let's head back to Cscape and take a look at how I implemented the logic for the high-speed counter. Okay, so whereas the high-speed counter configuration, there's probably a little less room there for variation from what I did. From the way you want your application to work specifically, there's probably quite a bit of room for you to program the application a little differently than I did. So the way I've programmed the application is this. On the first scan of the controller, I went ahead and turned on the high-speed counter disable function. Remember, we're doing that from logic. So the high-speed counter on the first scan is just sitting there frozen at its previous value. It's not ready for a trial or anything. Now, my next rung says this. When this particular high-speed counter disable bit, and I'm controlling that from the screen, remember I've got that push button on the screen. When that bit goes from on to off, I've got a negative transition one shot that's going to turn on to indicate I've got a new test started. And when I start that new test, I'm clearing out my previous calculations and setting a flag. This is just something I've chosen in my program. I'm setting a flag that says, hey, our test is now active. We're ready for that pumpkin to drop. Okay, and then while our test is active, as soon as that first photo eye trips, again, this has no impact on the high-speed counter, it's just we're following along in the program. As soon as this first photo eye trips, we set another internal flag that says, hey, our test is actually started. Our pumpkin is between point A and point B. And then once that's happened, and now the second photo eye hits, we're in another state that says, well, our test is complete, and we should have a new result in our latch value. All right, so when our new result one shot hits, we're going to do our simple calculation to take our latch value, convert it to a real value. Remember, it's a double integer as by default. We're going to divide that by 10,000 to get a millisecond value for our elapsed time. And then we're going to take elapsed time and we're going to do our simple calculations for inches per second and mile per hour because of the fact that the distance between A and B is fixed. And then once we're done with our calculations, we'll clear all those flags and disable the high-speed counter again, and we're ready for the next trial. Okay, so that's how I chose to program the application. You could have made other choices, but the high-speed counter setup, the one I chose, is probably the one that you would need to use as well. Okay, let's go take a look And I believe, yep, that's true. That's the end of what I wanted to cover with you today. So hopefully you found this informative and you now realize that not only can you use the high-speed counter to count with, you can also use it for precision timing applications. Okay, so we'll remind you that we're celebrating 10 years of the Horner Lighting Group. And for those of you interested in technology, the Horner Lighting Group is one of the experts in remote phosphor. And our remote phosphor videos are some of the most popular on our YouTube channel for the Lighting Group. And if you're really interested in technology, I would highly suggest you check out some of those remote phosphor videos to learn how that technology works, how it's different from traditional LEDs, and how you might be able to use it, especially if you do any kind of like surface finishing or paint inspection or any of those sorts of applications. That's a terrific application for remote phosphor lighting technology. Okay, there's still one more training class left. It's an advanced course next week. So if you're ready just to pack up and head to Indianapolis, we've got a couple spots available. Sign up really fast, make your travel arrangements, and come see us next week for advanced training. Now, next week on Tuesday at 2 o'clock, we're going to be doing a session on time math functions. So we're going to create some user-defined function blocks that you can use to do time math. Now, you may be thinking, what in the world would you use time math for? Well, here's an example. Let's say it's important in an application. Maybe you've got an agricultural application or a battery-powered application, and you want to know how long your controller has been powered down. Okay, how could you do that? Well, we're going to build a time math function that's going to do that very thing plus others. And you couldn't just use a standard timer or counter because the controller is going to be powered down over the period in which you're interested in the duration. So that's just one example of what we're going to show you next week for our time math functions. Okay, if you haven't done so already, don't hesitate to subscribe to our channel. It doesn't cost anything, and if you choose notifications when you subscribe, you'll be notified every time we go live or every time we post a new video. Okay, so until next week, let's all get out there and do us some good.